In the last lecture, we have introduced divergence function. We have proved that in a hyperbolic metric space, there exists a divergence function which is exponential. In this lecture, we will prove that in a metric space, if there exists a nonlinear divergence function, so then that metric space has to be a hyperbolic metric space. So first, let us recall the definition of this divergence function. So we say a function e from r greater than equals to 0 to r is a divergence function for a geodesic metric space X if for all points X and all geodesics gamma xy gamma prime xz, the function E satisfies the following. For all non-negative numbers, capital R, such that capital R plus R is less than minimum of the length of the geodesic xy and length of the geodesic xz. And if the distance between gamma R and gamma prime R is greater than E0 and alpha is a path in the closure of the complement of this ball of radius capital R plus small r around X, and alpha joins gamma R plus R and gamma prime R plus R. So then length of alpha is greater than ER. So in Euclidean space, so let us see what happens. So let us take the Euclidean plane with the Euclidean metric. Let us take a point X in E2. And let us take two straight lines. Coming out of this X. Let us call this point to be my Y, and let us call this to be my Z. And let us take, so let R to be equal to distance between X and Y, and also let us take this distance between XY to be equal to your distance between XZ. And let us take this angle to be theta. And now if I take some ball of radius capital R, and if I take any path which lies outside this ball of radius capital R, so then length of alpha is always greater than theta R. So what is theta R? So theta R is the length of this arc. So this will prove that, so this will imply that, so you can check that there exists a linear divergence function on E2. So that is geodesics in E2 diverge linearly. Okay. So now what we are going to show, so if there exists a nonlinear divergence function, so then that geodesic metric space has to be a hyperbolic metric space. Yeah. So this is my theorem. So let X be a geodesic metric space with a nonlinear divergence function E. So then we'll prove that the triangles are delta slim, and this delta depends only on E of 0. So E is the divergence function given, which is nonlinear. So let us begin with a triangle XYZ. So this is a geodesic triangle in X. And let us take this side XY geodesic, this geodesic XY to be alpha 1 and alpha 2 to be the geodesic XZ. So if I just write alpha 1 and alpha 2 as a map, so alpha 1, it is a map from this closed interval 0 dxy to x, and alpha 2, it is a map from this closed interval 0 dxz to x, such that this alpha 1 and alpha 2 are isometric embeddings. So it means that distance between alpha 1 s and alpha 1 t is equal to mod of s minus t, where this s and t, it lies in the interval 0 to dxy. And similarly for the map alpha 2 also. Okay. So now let us take this capital 2 be a number in the intersection of these two intervals such that this t is maximum for all small t belonging to this interval 0t, such that for all t, distance between alpha 1t and alpha 2t is less than equals to E naught. So I'll get a maximum capital T such that the distance between alpha 1t and alpha 2t is, it will be exactly equal to E naught. Yeah, so that is the thing I have written. So let x1 equals to alpha 1t and x2 equal to alpha 2t. So then distance between x1 and x2, so this is equal to E naught. So this is for the side xy and xz, and similarly we can do it for other two sides. Yeah. So we can split this triangle in the following way. So for this xy part, we got this x1 and x2 such that this distance is exactly equal to E naught. For y also we'll get this points y1 and y2 such that this distance is exactly equal to E of 0. And for the other side, other vertex z, there will exist points z1 and z2 such that distance between z1 and z2 is exactly equal to E0. And note that, so this possibilities can be also there. So x1 can be y or x2 can be z. So this possibility also remains. But yeah, for example, if x1 is equal to y, so this intersection of this geodesic xx1 intersection y to y, so this intersection will be non-empty. So x1, it will lie here, so the picture will be something like this. So even though this proof will work. Okay. Okay. So now the first case, so let us assume that this geodesic xx1 and this geodesic y to y, so they intersect with each other. So that is the thing I have drawn here. So we have this kind of picture. So this x1, it will come here. So this x1, it will come here, and yeah. And we have now, so there exist points x3 in the geodesic xx2 and y3 in the geodesic yy1, and a point P in this intersection of these two geodesics, such that distance of x3p is less than equals to E naught and distance of y3p is less than equals to E naught. So this P, it lies in this intersection. So here we have this point x1, and we have, suppose this point is y2. So P, we will get a point P, and we'll get a point x3 here, such that the distance between x3 is equal to distance between xp, and this distance between p and x3, so this will be less than equals to E naught. So note that distance between x1 and x2, so this is exactly equal to E naught. And if I take any point here, which is at a t distance, and take a point on this geodesic, which is at a t distance, so this distance is less than equals to E naught. So therefore, for this point P, I'll get a point x3 such that the distance between P and x3, that will be less than equals to E naught, and distance between Px will be equal to distance between x3. Similarly, for the other side, yz, so I'll get a point y3 on the geodesic joining yy1, such that the distance between Py3 is less than equals to E naught. Okay. So now, again, suppose, so this intersection is not empty. So it means that, so this point, so Z1, so in this picture, so it will come here. So Z1 will be somewhere here. So then you can observe that, so by a simple calculation, by applying triangle inequality, so distance between Z2, so this Z2 and Y3, so that will be less than equals to 3 E naught. So then in this case, so the life is simple. So this triangle, so this, you can show this to be 3 E naught slim. So we are done for this case. And now let us assume that, so this intersection between these two geodesics is empty. So this intersection is empty, and we have this picture here. So now what you do, so you apply the divergence function for these two geodesics. So you apply the divergence function for these two geodesics, and what you'll get, so you'll get a bound on the length of this path. So this path is union of geodesics. So it is this path is Z1X3, this geodesic, union the geodesic X3P, union the geodesic PY3, union the geodesic Y3Z. So in the picture, it is like this. So go to Z1X3, X3 to P, and then come back to the Z2. So using this divergence function, and also the fact that the distance between P, X3 and Y3 is bounded. So what you can prove that this distance between Z1 X3 and Z2 Y3, so they are bounded in terms of E naught. Yeah. So they are so the distance between Z1 X3 and Z2 Y3, so that is bounded in terms of E naught. So therefore this distance, so Z1 X2, this geodesic, it is a subset of the geodesic Z1 X3. So this distance will be bounded, and also distance between Z2 Y1, so this will be also bounded. So lengths of this Z1 X2, Z2 Y1 are bounded. So what we have shown that, so this distance is bounded in terms of E naught. So this distance are bounded in terms of E naught, and yeah. So from this, it follows that, so this triangle, it will be slim triangle, and the bound depends on the E naught. So for this point X2, so already we got a point here, which distance is exactly equal to E naught. And for this Y1, we got a point here whose distance is exactly equal to E naught. So this length is bounded in terms of E naught. So therefore, this triangle will be a same triangles, and the bound will depend only on the E naught. Okay. So therefore, we are done for this case 1. And the case 2, now suppose the geodesic joining XX1 does not intersect with the geodesic Y to Y. And if for the other sides, this ZZ1 intersect with the geodesic XX2, and the geodesic YY1 intersect with the geodesic ZZ2. So again, we can prove that distance between this x1 and y2, so this is less than equals to 3 E naught. So this will prove that, so this L1, L2, L3 are bounded. So what is my L1? So L1 is the distance between x1, y2, distance between y1, z2, and distance between x2, z1. So this you can check. So this is not very hard to prove. And if one of them is non-empty, so then again we return to case 1. So therefore, so what we assume here, so the geodesic Z to Z1 does not intersect with geodesic x to x2. Geodesic y to y1, it does not intersect with z to z2. And so our goal is to prove that, so this distances L1, L2, L3, so they are bounded. So if you can prove that thing, so that this triangle will be a slim triangle. So what we are doing here, so we are splitting this triangle in thin and fat part. So this part you can call it to be thin part, and here, so this part you can call it to be the fat part. And after that, so what will show that, so this L1, L2, L3, so they are bounded. So then this will prove that the triangle is slim triangle. Okay. Okay. So now suppose, so this L1, so this is the maximum of this L1, L2, L3. So if I prove that this L1 is bounded, so this will prove that L2 and 3, so that is also bounded. And let us also take this L3 to be greater than equals to 2. So let us take, so this A to be distance between x, x1. So this will be equal to distance between x, x2. B to be distance between y, y2, and which is again equal to this distance between y, y1. And distance between x1, x2 is equal to E0. Distance between y2, y1. So this will be equal to E0. Okay. So now let us take a ball, which I have called it to be B1, around this point X of radius A plus L1 by 2. And let us take the ball B2 around Y and of radius B plus L1 by 2. So this is my B2. So first observation is this geodesic. So this geodesic from X to Z, it does not intersect B2. Suppose it intersect. So then what? So then there exists a point U in X to Z intersection B2. So that point I have called it to be U. So this will imply that, so distance between Y to U, so that is less than B plus L1 by 2, because this U, it lies in B2, and U also lies in X to Z. And now suppose the distance between U and X is less than A plus L1 by 2. So that is U belongs to your B1. Then, so this distance between XY, we apply the triangle inequality. So distance between this X and Y. So that will be less than equals to distance between XU plus UY. And distance between X and U, so that I have that is less than A plus L1 by 2. And distance between UY is also B plus L1 by 2. So this distance is less than A plus B plus L1. And distance between XY, so XY is a geodesic. So is length of this geodesic, which is equal to A plus L1 plus B, which is this thing. So this is a contradiction. So this means that, so this assumption is wrong. So therefore distance between u and x, so that is greater than equal to a plus L1 by 2. That is, u does not belongs to your B1. So now we have assumed that, so this L3 is greater than equals to L2. So this L3, so that is greater than equals to L2, so that we have assumed. So from this, it will follow that, so there exists a point P in YZ in this geodesic joining Y and Z, such that distance between UZ and distance between VZ are same. So note that, so this U lies here. So U lies on this geodesic, and I'll get a point here, V on this geodesic, such that the distance between Z to U and Z to V, so these are same. So now this A plus L1 by 2, so this A plus L1 by 2 is less than equals to distance between UX. And if you go to this picture, so distance between U to X, so it will be, so U is lying somewhere here. So distance between UX is equal to A plus distance between UX2. So therefore, L1 by 2 is less than equals to distance between UX2. And so therefore, we have this triangle inequality. L1 by 2 is less than equals to distance between UX2. And distance between UX2, again, it is equal to distance X2Z minus distance UZ. So that is clear from this picture. Distance between UX2, this distance is equal to distance X2Z minus distance UZ. Again, distance between X2Z is equal to distance between X2Z1 plus distance Z1Z minus. Now distance between UZ is equal to distance between VZ. So distance between X2Z1, so that is equal to L2. And distance between Z1Z, so Z1Z, so this is equal to distance between this Z to Z. Minus distance between VZ. So L2, again, it is less than equals to L3. So this will be minus distance between VZ2. So V will be somewhere here. So yeah, so therefore we have, so distance Z2 minus Z minus distance VZ. So this will be equal to minus distance between VZ2. And L3 is distance between Y1 and Z2 minus distance VZ2, so which is nothing but distance between V and Y1. So what we have proved that distance between V, Y1 is greater than equals to L1 by 2. So thus the distance between V, Y, so which is equal to distance between V, Y1 and distance between Y1 and Y, which is greater than equals to L1 by 2 plus B. Now again again you observe this thing, so distance between V, Y, so this will be less than equals to distance between U and Y. So this will follow from this triangle inequalities. So therefore, so what we have proved that, so this B1 plus L1 by 2, so that is less than equals to distance between By, that is less than equals to distance between uy. So this will imply that, so this u, it does not belongs to this ball B2. So this is a contradiction because u, it belongs to B2, so that we have assumed. So therefore, so this geodesic, it does not intersect this B2. So this ball here, B2, so this ball, so it does not intersect this X2Z. So that thing we have proved so far. Yeah. So this ball, it does not intersect the side X2Z. Okay. So now we are in a situation to apply this divergence function. So now consider the path y2 prime to x1. So what is this y2 prime here? So this ball B2, so this is my ball B2, so it will intersect this side yx at the point y2 prime and the side yz at the point y1 prime. And now, so what path we'll take? So we'll take first this geodesic y2 prime x1. So that is this one, and then x1, x2, then the path x2, z1, then the path z1 to z2, and then the path z2 to y1 prime. So that is the thing I have written it here. So first take the geodesic y2 prime x1, then take x1, x2, then take the union the geodesic x2, z1, then take the union z1, z2, and then take the path z2 to y1 prime. Okay, so this path, it lie outside the ball B2 and its length is L1 by 2 plus E naught plus L2 plus E naught plus distance between Z2 to Y1 prime. Yeah, so this this distance is L1 by 2. So distance between x1 and y2, so that I have taken it to be L1. So this distance, it will be L1 by 2. So it's therefore its length will be L1 by 2. So this distance is E naught. So this distance is L2. This distance is again E naught, and this distance is Z2 to Y1 prime. So now we apply the definition of this divergence function. So E of L1 by 2. So note that, again, go back to this picture. So this distance is L1 by 2. So E of L1 by 2 will be less than the length of the path. So this is the length of the path. And this distance, again, it will be less than equals to L1 because L1 is the maximum. So therefore, we have this inequality here. And this is equal to 5 L1 by 2 plus 2 E naught. So E of L1 by 2 is less than 5 L1 by 2 plus 2 E naught. The left-hand side of the above inequality, so this is non-linear, whereas the right-hand side is linear. So this proves that this L1, it is bounded in terms of this E naught. So therefore, L2 and L3, that will be also bounded because L1 is the maximum of this L1, L2, L3. So therefore, what we have proved that So we have proved that this L1, L2, L3, so they are bounded in terms of P naught. So therefore, this triangle, so this will be a slim triangle. Okay, I'll stop.